Good morning. If you haven't already started, the question should be on cool. You have 15 minutes. These are the same questions as on NTU Cool, right? So if you cannot see it in the back, you just look at your screen. There's nothing new here. I'm not sure why I'm putting them. Just kind of, to fill in the projector. Show a picture of a cat if you like. Oh, what's your name?
My name is Stanley.
Oh, you're Stanley. Oh, nice to meet you. Welcome. You were my last subscriber on YouTube. Now I have no more. So these are the same questions that you have on NTU Cool, and you have 15 minutes to start, like from when you start to finishing. Meaning even if you start now, and I'm going to start talking pretty much now, you can still finish the quiz. Here's another one. All right. I got 50 students, so I can check in real time how many students handed in the quiz, and it's 50. So that's normally my, threshold. So if you still need time, you still have, you have 15 minutes from when you started. It's just that I'm going to start talking here. So first thing, I sent out an announcement just like 10 minutes before the class that we're going to have a midterm. And it's on November 10th. November 10th, 1110. 11, what's the year? 109? No, it will only so that's a good question. It will only cover the stuff that we are covering on mechanics. So we will switch the week. So we still have 2 weeks. So we are on the 22nd. So we have the 29th, where we're going to wrap up mechanics, and then we have one more class on the 5th. Where I'm probably going to start talking about electrics. That doesn't mean that electric forces will be in the exam. It's only going to be everything about mechanics. You remember we're covering chapter 12 today and 13 next time, and I think that's all. Gravity. So nothing. I think, yes. You can check NTU Cool. You see there's a jump between the 10s, like the chapters with like 10, 13, maybe 14. I'm not, can you check or I check? And the other ones being like everything before chapter 20 that we covered, okay? There's a big distinction there because we skipped a lot of chapters, okay? So it means that only the chapters that are in my syllabus will be covered. Okay, you don't have to start like worrying about rotation or things that I didn't explain. Please. We are. chapter 10 is which one? That's rotation, vibration. All right, I'll pull it. Let's hope that I got the syllabus. All right, so this was my introduction slide, right? And I was showing this one here. And so after gravity, we're done. Everything else is volume 2. The saga continues. Okay, questions about that? I also, in the announcement, I'm stating this should be on NTU Cool. Everything that I'm displaying here should be on NTU Cool. So there should not be a need for you to take pictures of that thing. Unless you really want to, I don't want to keep you from it. But so we are going to finish today part 1 and hopefully start part 2. But there's only 2 chapters, right? We already covered 1. So the last chapter is 13, and then we're done with mechanics. So yes, we have skipped rotation, rolling, waves, oscillation, everything that is somehow related with going back and forth or around will not be covered here. Oh yes, right. So in my announcement, I'm saying you're allowed to bring a calculator, pens and pencils, and a cheat sheet. A cheat sheet is an A4 formula sheet that you can put anything you want on. Derivations, formulas, poems, recipes, whatever you think is going to be helpful or entertaining. Somebody brought a pillow. And I still don't understand why, because it's just 1.5 hours. Like, also, if you're done, you are welcome to leave. Okay, so it's not like I'm making you sit here. It's going to be at the same time, so 10:10 till 12:20. But it's not going to be in this room, right? Because today's Thursday. We're going to be in 303, which is the bigger room, so that I can keep you at socially distanced distances. Minimize the conversation between you guys. Other questions? I mean, if you come up with questions, we still have 2 recitations and almost 3 weeks, so you can contact me. Right, okay. So we are going to cover everything from chapter 8 and 9 and 12. Right, 8, 9, 12, I think, yes. So we started introducing energy last time, and I was saying it's really useful because there is a simplification, and that is conservation of energy. No matter what happens with energy of a system, it cannot be lost. It can be converted. And so we introduced kinetic energy last time as the energy of something moving. And we found that that was already pretty useful just by itself, because we found that in a force distance diagram, we would just get work. And work is the only thing that can be converted into kinetic energy currently. Now we're introducing a second form of energy, and that is potential energy. Potential energy is a property of a system. You need more than one object for it. Kinetic energy just needs one object, right? You throw it, it has a mass and a velocity, that's all. But potential energy needs 2 objects. For example, you throw something on the surface of the Earth. Earth is the one thing, the projectile is the other thing. And so as you throw it higher, it converts its kinetic energy into potential energy. And that means as it gets dropped, it goes the other way around. And so we can now convert work to kinetic energy and kinetic energy to potential energy. Right, so let's see that. So yes, you have to do work to increase potential energy. While work is being done when you decrease it. Okay. Oh yes. One interesting point is that we can now categorize our forces. We have introduced a lot of different forces: friction, gravity, spring force, drag force. So we can categorize them in conservative and non-conservative forces. Conservative forces are nice, non-conservative forces are annoying. Conservative forces means that they are not wasting mechanical energy. So for example, me lifting something against gravity and then it dropping again will get me the same work. I put the same work lifting it as will be done by it dropping. So for example, that means the speed at which I throw it up will be the same as the speed at which it comes down at the same position. So that's nice. Mechanical energy is retained. But that's not really true, right? Because we introduced the terminal velocity last time. That means no matter how fast I throw this thing up, it will not come down at exactly the same. It will not come down at that speed. It will come down at terminal velocity. And so that's kind of annoying, right? Because we would have to now consider how far did it travel? Did it reach terminal velocity? And so non-conservative forces are forces that don't maintain mechanical energy. So that means that as a physicist, I will try to avoid non-conservative forces because they're hard. And so means that I'm mainly interested in dropping stuff in vacuum because I'm scared of calculating friction. But once we do that, it's nice because we don't have to worry about the path that something takes. Before we had to calculate what's the acceleration over at every point in time, and I get the velocity at every point in time, then I get the position at every point in time. What if I don't care about the position? And that's what conservative forces are nice for. No matter if I go from A to B on path 1 or on path 2, let's say so we need to do work against gravity, so I'm lifting something. It doesn't matter if I walk along that way to lift it, or if I first go through that gravity and climb up a steep slope. The work that has been done, me lifting, is just going from here straight up and going over. Any path will work. And so that means that we can simplify our calculation significantly. I don't have to worry about, this I get a sign, and then the sign changes, and then it changes again. I always have to worry about the components. Instead, I'm just saying, I'm going to move up to here, and everything else, up to here, everything else doesn't require me doing work against gravity, at least, right? Because I lift it onto a shelf, and then I can just slide it over a shelf. Now you're like, well, but sliding takes friction. No, friction is a non-conservative force. I am just forgetting about any kind of friction. So that means me moving this over here is the same thing as me moving this over here and then not doing work anymore. You're like, no, you're lifting it. You're clearly doing work. You cannot keep holding this forever. And that's true and false at the same time, because I could just be replaced with a shelf, right? And a piece of wood is not doing work. So yes, I am doing work lifting this, and it starts. But that's just because I don't have a shelf lying around. So just holding something at a certain height does not do work, because it has to be force moving something at a distance, right? That's how work was defined. So conservative forces are nice because I can pick the simplest case for calculating them. So that means everything we have learned about kinetic energy. We were saying kinetic energy is, the difference in kinetic energy is work, right? Now we're saying the difference in potential energy is work. Nothing has changed. And so we said work would be force times distance unless the force changes over the distance, right? And then we have to worry about an integral or calculate an area under a force distance curve, right? That's what we did last time. All right, so nothing has changed. We can, for example, calculate the work due to the force of gravity, because gravity doesn't change, at least not from here to there. So me lifting something means I work against the force and I lift it by a meter. So it's the force of gravity times a meter. And you remember force of gravity or weight was just mass times gravitational acceleration. Okay, so we're going to try something more complicated. We already calculated that last time. We calculated what work has to be done to deform a spring. Right? You remember the force on a spring is my distance with my force. The force deforming a spring gets higher the more I deform it. Right? I have to push harder and harder to make it go inside. What was that law called? It's the only thing that is not Newton's law, it's Hooke's law. F equals k times x, right, where this one is k, which is the spring constant. Right, so we calculated that the work would be force times distance if the force didn't change, or it would be the area under the force distance diagram if the force changed. Right, so this area here is not a rectangle. If I were looking at gravity and times E, it doesn't depend on x, right? So here the area between them is simply force times distance, but the area of the spring of the work done on a spring would be 1/2 kx times x. Kx is this one times x is that one, so 1/2 kx. Right? Okay. So we got that one just by analogy. Okay. So let's do it. So this one is 8 kilogram stone, and it's deforming this by 10 centimeters. And so my question is, what's the change in gravitational potential energy? Oh yeah, the stone is pushed down. What is the change in gravitational potential energy? You take the stone, you push it down, it goes down 10 centimeters. You push it down 30 more centimeters and let go of it. How high is it going to fly, basically? Go. Oh. You're scared of change in gravitational potential energy. Then just calculate this one. This one is easier to communicate, right? What is the maximum height that the stone will fly up after you push it down 30 centimeters and let go? We do it like always. You have 5 minutes to get your initial idea. I will give you like the ones that need a nudge. Give them an idea, and then I give you another 5 minutes to solve it. Okay. No, let's do the height. So in case you need some inspiration, there's two ways of going about that. You remember you can just do a force balance, and you get the force as a function of position, which is, I'm not sure, it's kind of too complicated for me. So what I would like to do is just have energy balance, right? At what point do I provide energy? I only provide energy here. This is me pushing down the string. So this is the only work that takes it from its equilibrium position, like where it's happy, on, no, sorry, its equilibrium position where it's happy is this one here, to flying up. So the work that I'm doing would be the work that deforms the spring, right? The only question, and I deform the spring by 30 centimeters, fine. So I know the work that I have been doing on the system. Now the only question is, what's the spring? The spring is not given, right? So maybe that's why they gave you such a complicated multi-step thing. First, you take the stone and let it rest on the spring and it deforms. Then you deform it some more, and then you let go of it. Not sure if that's helpful. Please. Say it again. When is it equal to what? The spring is, so this picture at rest shows that the spring is already 10 centimeters compressed, right? Because it has a weight. The weight itself is deforming the spring. So you're asking at what point is what's the release point? I think this is the release point, like when it's already compressed, 10 centimeters. But you can do it from any point, just keep track of it, right? You can say it's going to be 30, or I don't know, 60 centimeters below the lowest point. Or if you consider this to be 0, it's going to be, well, this was 60 centimeters, and like this 20 centimeters from that point. So just specify from where you're checking. So they're considering this as the release point, right? So the release point would be here. When basically the stone is not resting on the spring. So we can consider this one. Well, what I would start with is maybe going from the back. The back meaning what I'm interested in is H, which is the potential energy that has to be overcome. I have to provide that energy in some form to be stored in potential energy at a height H. Right, so I could throw it, or in this case, I push down the spring, and then it goes faster and faster until it lifts off, and then that energy is being converted into potential energy. So the spring is deformed first, and then it gets longer and longer until it lets the ball lifts off. So at this point, it had some velocity that I don't know and don't care about. What I care about is from that point on, all the energy of the ball is going of whatever I did to it before is going to be stored as potential energy. And at the highest point, it doesn't have any kinetic energy anymore. The whole energy that was inside the all is now potential energy. So that's what this formula means. This height means that all energy that was in there is now potential energy. So I just have to find out what was the energy before. Because after, it's just mgh. So the energy that was in there before is kinetic energy. But I don't know how fast it went. What I know is that it went from elastic energy into kinetic energy into potential energy. So I can skip this. This is a nice thing about energy conservation. I don't have to keep track of all the forms of energy that it went through. I just care about, well, what did I put in it? I didn't make it go faster. I just pushed down on the spring. So that means that the energy before was elastic. And the energy after is mgh. So that means 1/2 kx squared, where x is displacement, right? Maybe delta x squared would be mgh. Nice, I'm done. I displaced it by 30 centimeters. And I know mass and gravity, so I can solve for h. H is 1/2 kx squared over mg. What's the problem? What do I not know? So I know x, right? That's 1/2 times 0.3 meters over 2 times, what's the mass? 8 kilograms times 9.8 meters per square second. What am I missing? K. I don't know the spring constant, and they didn't give it to me. I mean, I can estimate that that looks like a stiff spring because it's gray. Must be metal. So that's what I'm still missing, K. What else do I know that can get me K? I know that under its own weight, it would deform it by 10 centimeters. And again, there's two ways of going. It could be a force balance. The force balance would be, where did I put it? I guess nobody's watching on YouTube anyway, so. The force balance would be K times X. The spring force is being opposed by M times G. Or if you want to say with energies, which I like, we could have an energy balance, which would be the potential energy that this thing had is being converted into energy of deformation, right? So mgh would be 1/2 kx squared of k h squared. 1/2 k final minus. Oh, this one here is average. It's h final minus h initial. So we have half and half. We have h and h, h final. So we would get the same thing. Kx equals mg. All right, so we know k. K is that, I don't know, we'll call it x is 0.1, is 8 kilograms times 9.8 meters per second square over 0.1 meter. Right, 0.1 meter? Yes, it gets moved down by 0.1 meter. So, all right, so that K, and I can plug it in there. I have H. Questions about that? So this is the power of energy consideration. I don't know how fast it went at any time, but I don't care. What happened is that, yes, at this point, everything was kinetic energy, but I'm not interested in that one. I am interested in how it went from here to there. And all the energy is being converted. 0.3 is that's the stone being pushed down. I pushed down the stone by 30 centimeters. That's the only energy I put. I didn't make it go 0.1 down. I didn't lift it up, right? My only contribution is 30 centimeters down. That's me doing my exercise today. Because I didn't move at 0.4. I moved at 0.3. Gravity moved at 0.1, right? That was not me. And so that one is not going to be important. So between the release point and the rest point, it moved by 0.1 meters by itself, right? This is its kinetic energy, its potential energy being converted into elastic energy. But on the way up, that elastic energy is being converted back to potential energy by itself, right? So I am not the one doing that work. The only energy that I am adding to it is my deformation work. And so we find that if we do k x squared over m up there, we get 80 centimeters. Oh, and the spring constant was 780 Newton. All right, cool. So why did that work? Because no matter what happens in between, kinetic energy, elastic energy, and potential energy can always be converted into each other without loss. What happens if there is loss? Right? We have considered that any kind of work would either make it go faster or might make it go higher. What if that's not all of them? So that's the problem for non-conservative forces. In those ones, your mechanical energy, kinetic and potential energy, elastic energy, are not being conserved. We haven't considered air drag on this, or the fact that if you deform something, it gets warm. So normally, not normally, for realistic pictures, we have to consider other pathways where energy could be converted from mechanical energy. So heat. And so that would mean that mechanical energy is not a constant, it's not conserved. So work being done on a system would now probably be converted into some mechanical energy, but some of it is not. I'll explain what I mean with another example, given the time. We'll try it. Let's see how fast you guys are. So, we're sliding this block. And this block, so we give it an initial velocity of 6 meters per second. So it has some initial kinetic energy. And so you would expect that as it goes down here, it goes faster because it had some kinetic energy and it had some potential energy. And then it's going slower because now some of the kinetic energy has to be converted into into potential energy. But then it's sliding on this gravel bed. So now it slows down, even though its energy is not being converted into potential energy, and it's not being used to deform something. It's just slowing down because it turns warm, right? So the question is, and I give you a friction coefficient, so you know that there is a constant force acting against its motion, and I want to know how far it slides before it stops. Go. You need a hint, or you just need more time? All right, more time. You want a hint? That's a good question. In general, I'm pretty cavalier about numbers. I don't really. So the question was, what is the correct G, the gravitational acceleration? And coming from Germany, I would say 9.81. But coming from Taiwan, it's 9.803 or something. So anything 9.8 is fine. But you can. I'm always expecting that you write the variables first. So you have an equation, and then you put in the numbers. So even if you go with 10, as long as you say, I assume G to be 10, you say G, 10, then I'll take it. Unless it's completely off. You're like 500, then I'll be like, yes. Yeah. Also, if you need constants, I will provide them. I'm not sure about G, but let's imagine in the exam, you're like, I'm drawing blanks. I don't know what G is. I should be giving you that number anyways. We're not testing numbers, okay? I don't want you to remember anything except for G. So in general, in the exam, if you think that there is a number missing, raise your hand. Most of the time, I miss a number. Like pi. Okay, you're like, I don't remember pi. I don't have a calculator. What about this one? What would be the energy at this point before it starts grinding to a halt? Will it be faster or slower than the initial velocity? I mean, it goes faster, it goes here, it speeds up. Will it be slower up here? Okay, if you say yes, you have to tell me why. Why is it getting slower? So here, it only has kinetic energy. Here, I don't care about any path, right? It's frictionless, it's it's conservative. I don't have to worry about the shape of it. That's the other thing that you might have asked, right? What's the slope? I don't care what's the path. I know that now my kinetic energy is going to be reduced because some of it got converted into potential energy. Does that help? Well, what is the energy that it has at the very end? What's the energy that it has at the very end? 0? It's not 0, it still has the potential energy, but all the kinetic energy got converted into it. All the kinetic energy got lost, right? It has 0 velocity, but it's not at 0 height. It's not like an incline, it's not like an incline. So its kinetic energy first got reduced by potential energy, and then it got reduced by what? By some kind of heat, right? All the what friction does is it converts mechanical energy into heat. So now the question is, what would be the how do we calculate the heating? Well, you remember that any kind of this one is work being done. And how do we calculate? So I call it thermal work. Work being done to heat something up. And what is the definition for any kind of work? Force times distance. What's the force? Friction force. Friction force, does it change with distance? It doesn't, right? It just depends on weight. it depends on friction coefficient times normal force. But fortunately, the normal force is like the normal is in y direction, so it's gravity as opposed to probably weight. So the energy balance would be kinetic energy in the beginning. So I'm only interested in this point, beginning, and that point, end. All the kinetic, is there still kinetic energy left? No. Was there potential energy before? I mean, sure, you can put any energy, any height that you like, right? But whatever that height is, it will show up on both sides. You want, all right, fine. You could say there's potential energy, G, height over normal wall, height of a classroom. What would be the potential energy afterwards? Well, it's a classroom plus mg, what do we call that? H. Is there kinetic energy left? No, it stopped. But it used up thermal energy. So wouldn't have had to put those in. I just wanted to, for completeness reasons, say I don't have to assume that this is at zero height. I could assume that this is at any height, but this one is 1 meter taller than before. So this is a potential energy that the kinetic energy got converted into. Right? So we have 1/2 mv0 squared. The kinetic energy at the beginning is mgh plus mu times mg times e. It's scraped over the floor for D against this kind of force. This is a friction force. So that's the work that was being converted into heating up. So I can solve for D, right? I don't want to solve for D. I'm already behind. Questions about that? What's the importance of energy balance? It doesn't matter what path it's taken. The only time that the path matters is if we're considering non-conservative forces. Right. So yeah, you see the masses cancel out. It's kind of neat. It means that we didn't have to worry about the weight of this thing. It will always slide at to the same halt. Depends on the friction coefficient and G, and so you're getting 1.2 meters. So that's all I wanted to say about potential energy. Oh, no, that's not true. I have one more. Potential energy, the relation of potential energy distance curves and force distance curves. You remember I was gushing about force distance curves, that they're useful in calculating work. And so now we have work distance curves. So it probably means that we can relate the two. So from a potential energy distance curve, we can get the force. It's just a slope, which makes sense, right? Because force distance curve, the area was the potential, was work. And so why is that important? Because we can read off important things. Like, for example, if we start an object here and it goes down this complicated route, where is it going to end up? How high is it going to how far is it going to travel in this direction? This is a potential energy distance curve, which means nothing more than a height distance curve, right? So this is a direct representation of a mountain. So you are pushing something down the mountain, it goes over that little ridge, and then how high is it going to come up here before running out of steam? Well, it's going to come to exactly that height. It doesn't have any other energy. All the energy is potential energy, unless you gave it some kinetic energy first, then it might be able to clear that. If you just started with zero velocity here and let it go down, it can only get to here. This is its turning point. It cannot get higher than that. It will go slower and slower and slower until zero velocity, and then it will go back. So this is useful, right? Because you know that there's a force acting on it that way. There is a slope. The slope of this is negative. This is a minus d u dx, so the force is pointing. Sorry, the slope is positive, the force is pointing downward, right? Makes sense, because it's a hill. So something is making you go down. There are a couple of interesting observations. How about here? Is it getting faster or slower? So you're coasting down here. What's happening here? Are you going faster or slower in this stretch? You're not varying the energy, right? It doesn't change its energy from here to here, meaning there's no force acting on it. The slope is zero, or minus zero. And there is no force acting on it, meaning it's not speeding up. That kind of makes sense. Imagine you're on a level part of the track. You're not going faster or slower, unless friction or you're adding more energy, which you're both not. So flat areas mean that no force on it. So if I put something here, it's not going to move, right? What about if I put it here? This has a slope that is flat, right? This is weird. This one we kind of understand. But see up there, if I just balance it exactly on that mountain, it will not experience force. So this one is equilibrium, right? It doesn't change. This one over here is equilibrium as well. It's just that if there's any kind of perturbation, any kind of shaking, this one will just not care, right? It will just stay. It will slide a little bit and then it comes back. But here, if we do anything to it, it will just fall down. So this is an unstable equilibrium, and this one, well, somewhat more stable. If you had a complete valley, then it would be a stable equilibrium, because pushing it out that direction, it just comes back there. Opposite of that, try to balance a ball on a ball. It works better if you consider friction, right? That's why you can balance balls on balls. So questions about potential energy curves. There's literally height representations. Okay. So what I've done with energy is we're going to do more on energy when it comes to more complicated forces. Right now you're like, oh well, I could have calculated my normal force, my friction force at any point in time, and see how it slows down my object on the gravel bed. So you could have still done that with force balance, but we're going to see more complicated forces where these potential energy curves really come in handy. You can imagine for planetary motion, you don't want to, once we get into more complicated gravity, you will not want to calculate it by force balance. You want to have some kind of easier tools, especially in vacuum. You don't have to worry about friction, right? So Okay, all the forces up there are conservative. So, all right. So we have done energy, and we found that the slope in an energy position diagram is simply force. And so you remember how we got from work to power? It was just force times velocity. So we could do the same thing here, force times velocity. So we can get power out again. Power means the change of work with time. How fast are you applying work? So we've done that for kinetic energy already. So questions about energy, because we're going to come back to it in chapter 13. And again, in electrics. Please. Yeah. We are calculating the work that is being done, sliding it over. So any kind of work is the force acting on it times the distance that you have to displace it. So this was not, we were not trying to do simple math or simplify math. We were doing energy balance, and so this one is kinetic energy, this is potential energy, and this is work. You can basically make up your own energy, right? We didn't know that what's the form of thermal energy, but we said all our thermal energy is being converted, or like, what is it? The only way that thermal energy increases is through work. So the work being done on the object, or being done by the object, is converted into thermal energy. So any kind of work is force times distance, assuming that the force is a constant over distance. So this will not work for drag. So you see, the most realistic picture would have been I push something or I throw something and I see what's the velocity after some time being lost to drag. But that's hard. This is nice because the force for friction, for sliding friction, is just a constant, just depends on weight. Drag, you remember, depends on velocity. So that makes it really, really annoying. So it's a non-conservative, velocity-dependent energy. It's very, very annoying to handle. So even the simplest projectile motion, we cannot calculate. Other questions? Please. So basically work is a currency. You doing work means you're increasing the value of the object moving. And then that one can waste its value in converting it into thermal. So basically thermal energy is a waste of energy. It's a waste because so you would have to do work, and it should go towards making it go faster or sliding it higher or something, but instead it just heats it up. You're not getting that energy back. And so yes, the currency that you're introducing is work, but it can be converted into kinetic energy or potential energy, or in thermal energy, or other ones, because there are still other forms. For example, you could be doing work and cranking, I don't know, like the handle of a whipping cream machine, and what you would get out is more fluffy whipping cream, right? So you can change there are many kinds of internal storage for energy. More creamy, colder, warmer. But they all come down to we are putting in work. So it's a simplification because we don't really care what's happening inside the system. We're just like, if it's non-conservative, it's lost to mechanics. If it is conservative, we can get it back. All right. So everything that we've done up to now is thinking about atoms. You have probably not thought about atoms, but we have assumed no drag, no friction most of the time, because the particles, because we started with the simplification that we're looking at into infinitely small particles, right? And so we want to make it a little bit more complicated, if you want, to consider more real objects. So real objects have a size, and they have a shape. And so That's horrible, because now we would have to consider the force balance for every part of the object. There is good news, however, most of them are going to be uselessly simple, trivial, because most of the forces will be inside the object. So I would like to figure out a simplification. I want to treat big objects like particles, plus some additional bonus behavior. And so that brings us to center of mass. Center of mass means even if your masses are not equally distributed, like it's heavy here and light up here, the center of mass is like we can simplify this one into a single particle, which is containing all the mass of this, and whose position is the center of mass. I can make a complicated object into something simple when I just break it down into its center of mass. Why would that be useful? Because if I were to throw that, and I don't, it would have a complicated motion. It would probably tumble. Its center of mass will behave like the particles that we already calculated. So we can we can split the problem. We can split the problem with, well, on average, it will behave like a little particle, plus there are other things that we still have to consider. And so center of mass is simple in in one dimension, right? Imagine you just have two masses separated by d. Where imagine those two masses to be the same. Where would be the average mass centered? Would be the middle, right? And what would be the mass of that particle that could describe this whole system? Would be twice the mass, m1 plus m2. So I can say the mass of a particle with a particle that is positioned here and has the sum of both masses will behave the same way. I'll explain what behave the same way means in a second. So from that we can kind of guess how to calculate the position of the center of mass. We know that the center of mass should be 1/2 d if m1 is m2, right? Assuming m1 equals m2, then x center of mass would be 1/2 d, right? You're with me on that? Or you just 20 more minutes, we're done. Center of mass, yes. So what would happen if the masses were not the same? Well, it has to simplify to that form. So if I put some kind of mass in there, what would that be? M1. It has to come down, it still has to be, there has to be a d in there, just for the units. And I probably have to divide by mass, because else the units wouldn't work out. So m1 over m1 times d, would that work? No, because if m1 equals m2, then this one should give me back 1/2, right? In that case, this one happens. This one doesn't. Well, how about m2 over m1? No, it's still 1 over 1. So, now it would work. So that's the simple approach to getting that formula. You also realize that this is kind of annoying because we are assuming that one of them is just at 0, one is d away. What if we have more particles? Then we cannot really say that this one is the most important one. It should be at 0, right? So I would like to add x to that. It doesn't change the result. It should still be d half away, except now from that point I have the x1 plus d half. So this is just a complicated introduction to that formula. This one is for an arbitrary choice of origin. Okay, so with that we can do it in components, right? So we have center of mass of x and y and z, then we can do it for as many particles as you want. You can simply calculate mass of the first one times its position plus mass of the second one times its position over the total mass, or the mass of the particle, basically, that you want to get out. So center of mass is easy to calculate, at least. Why would it be useful? Yeah. Let's do this one. This is a complicated one. It has 2 stars. So we're looking at like a projectile being shot, and that in the middle of the of its trajectory, one part is just dropped. This is kind of like a rocket stage, right? Rocket stages work by you just dropping parts of your rocket when you don't need them anymore. So that means that you would expect that this one flies until it hits the ground, right? Question is, how far does it fly? Hopefully farther than if you hadn't ejected your rocket stage, otherwise it would be pretty useless. Okay, so my question is, how far does the gun go? How far does a projectile go? All right. Let's do 5 minutes and then think about it together. Just in case you need it, I'm not sure. This is what we found for the range of a projectile. I'm not sure if it's useful at this point, so that you don't have to look for it yourself. This is not this. Okay, you're like, oh, you just solved it for me. No, this isn't assuming that this thing is sticking together, right? This one, we never considered that the projectile would break in the middle. So I'm not sure if this one is useful. I just want to offer you some assistance. there's two ways to think about that. And you're probably stuck with the first one, which is, well, at some point up here, basically the first part launches from the second part in a way that this one falls down, right? This is really complicated because it's not that, like, the problem is the observation that this part falls down like without any velocity. How does that happen? It must have somehow got slowed down, right? How does it get, this rocket part has to get slowed down compared to, like it would have just flown by here, right? Without any, without any forces acting on it, it would have just followed that trajectory, but it didn't. Instead, it just fell down, straight down. So that means that this one somehow pushed on it hard enough that it stopped, right? You remember Newton's third law. If this one is going zero velocity, this one must have experienced some kind of acceleration. It was at a constant velocity until it decelerated to zero, right? So this is complicated because now you have to consider, oh, so what's the acceleration of this guy? Or what's the force necessary to make this one go to like stop? So this is hard and it's unnecessary because you remember that a center of mass takes a complicated system and describes it as a particle. It describes it as a particle without you having to work under kind of internal forces. We don't care about the internal forces. We're only caring about the external forces. Under an external force, the center of mass will move like a particle, being subjected to that external force. So imagine, forget about this. What would the center of mass of our projectile do? Where will our center of mass move? Or where will it touch down? The center of mass at the beginning was probably halfway between the two parts, right? They're the same mass. And so what will happen to that center of mass? It goes on a projectile route. We only introduce external force one time and one time only. We kick it to fly. After that, all the forces are internal, right? Sure, there is something pushing against something, but both these parts are part of the of our particle system, of the body. There's constantly stuff like forces on your body, otherwise you would fall apart, right? That doesn't mean that it affects your motion. There is a ton of internal stress on your bones just from torsion. That doesn't mean that this is affecting you moving. Like if I drop you from a window, okay, that is a bad example, but if I were to drop something off a window, it doesn't matter how much internal forces are, right? It doesn't matter how strong it is or how badly adhered stuff is. All that matters is if you dropped it, it's going to land on the floor. Imagine the center of mass of a firework. A firework will explode in 1,000 pieces, but the center of mass would just go up and go down. All the pieces will, like, if there's no other external force acting on it, the center of mass doesn't change. And so the same is true here. If the object had stayed together, it would have been around the center of mass. But it doesn't have to be. No matter what happens to the object under its external forces, the center of mass is still where we would expect it due to external forces. Internal forces don't matter to mechanics. So this is important because we already know where the position of the center of mass would be, there. And we know where the position of x1 is, there, at whatever the position of this guy is. So that means we know where the position of x2 is because we just solved it. x center of mass is x2 m2 over x1 m1 plus x2 m2. Oh, m x2 m2 over m. M2 plus M. Right? We found that this is the center of mass position. So now all we have to find out is what is, so we know this one is where we left it. That means this one must have traveled twice, or it must have traveled farther for the center of mass to end up there. So can we calculate it? We can, but it doesn't add anything. So this one from here to there is 35 meters. And so we can, by symmetry, we can see that the highest point is at half, right? It's a parabola. So it traveled, the first part traveled 17 meters. 17.5 meters. The center of mass traveled 35 meters. How far would x2 travel? Well, it would travel 17 meters farther. From here to there, 17 meters. So from here to there, 17 meters. Otherwise, it wouldn't be the center of mass anymore. So that means there's a hard way of solving it, considering that in order for the first part to slow down, the second one has to take up its energy. And so we're basically calculating a new shot from the top with twice the velocity. But that's horrible. You see there's a ton of math involved. Alternatively, you can just calculate the center of mass and you get to the same number. So you see the simplification of distinguishing between external and internal forces. Okay, so simplifications are useful. And there's one more simplification that would help us for that projectile. And that is, so you're saying, we can say the kinetic energy has to be retained, right? We can say the thing is flying and the kinetic energy within the system has to be retained. But that's not a lot of fun. Basically, we could have said, oh, the kinetic energy of this one splits into the kinetic energy of this, which is 0, plus the kinetic energy of that one. That's not ideal because we're not taking advantage of internal and external forces in this case. So instead, it would be nice if we had a similar simplification for forces, as we are similar simplification for energy in a system, as for forces in a system. You understand what I'm trying to say? We have said forces, we can distinguish between external and internal forces, and then only care about the external forces. They will act on the center of mass. It would be nice if we had a similar idea, a similar approach for energy, because then we could say, whatever the energy of the system is, I don't care. I only care about what I added to it through an external force. And so this would be kinetic energy, potential energy, elastic energy. So instead, it's hard to distinguish them between external and internal parts. So instead, we're introducing a new concept. See, this one kind of looks like kinetic energy in that it's a material, it's an object property. So we're saying any object would have a linear momentum. Linear momentum means if it has a mass and a velocity, it has a linear momentum. And that linear momentum can only be changed by force. The same way that we were saying that energy can only be changed by work. And so this is actually the correct version of Newton's law. Newton was never saying F equals ma. He was saying the change in linear momentum with time is a force. Or if you want to change linear momentum, velocity, you need to exert a force. So yes, if you look at it, you can say, well, dp dt means we take the time derivative of this, but that's just d dt mv. And if mass is a constant, then it's just dv dt, or acceleration. But this is more general because mass doesn't have to be retained. We could still calculate this for a rocket or for a projectile where the mass decreases with time. So the usefulness here, and we're going to pick that up next time, is that we can say that only if you apply a force over a certain time, you will get a change in momentum. We don't care what's happening inside the system. If I have an external force applied to any complicated body, it will change its linear momentum if you apply force for a certain time. And so this is going to be useful if you're considering complicated systems that you know something of. For example, in the case of billiard, you know that the initial velocity of them was 0, right? Their center of mass was at the center of the table. And then you're applying external force exactly one time for a certain short amount of time when you hit the snooker balls with a cue. So this is the only time that you change momentum. If they're slamming into each other, they're changing their internal momentum, fine, but I don't care. I can just keep track of the external momentum to find out what's the average position, what's the average velocity of all the balls. Or if I am interested in internal, like in the motion of each ball, I can do that as well, because I know the internal momentum cannot change unless external force has been applied. So if two balls smack into each other and they're breaking into 15 balls, all with different velocity, it doesn't matter because I know the total linear momentum, the total sum of all the masses and velocities have to be equal to the impulse that I provided. So we're going to see that that is useful for collisions. So we're going to do that next time. For now, questions about what we tried to do today. We introduced a new form of energy, and we're starting to look into how we can simplify more complicated objects. Where we're going to take that? Well, we're going to see, so we're now interested in internal forces, so we're going to learn about materials and their internal forces. And then the last part is going to be on the biggest systems that we have, star systems. So that's going to be chapter 13. And after that, we're going to go review everything. So next week, I'm going to introduce chapter 13 and wrap up all mechanics. And then we're going to electricity. Is electricity going to be in the quiz? No. When is the quiz? 10th of November. Where is the quiz? 303. All that should have been an announcement that you got today. So questions? No questions? Thank you for coming. See you next week. Yes. Okay. So this one is the velocity x direction. So when you're shooting up, you're basically breaking it down so that it goes that way. Because if it were going any other angle with bounce, like this one would not just have zero velocity. So the question is, what is that new starting velocity? And so it is this old starting velocity, but now it's 2 times. It's 2 times because half of it goes twice as fast because the other one we know stopped. Make sense? Yeah. Yes. Yes. So you have your okay. So have you both been inside the game? So you've seen that I give a key all time, and then I collect the answers from recitation. Are you inside the group already? Recitation group. Thank you. I am not sure how that works, but we can check here. So I am currently on YouTube, which is pretty cool, end screen. And I thought that I made an announcement in NTU Cool